Hello and welcome to the last chapter in our unit, Chapter 15, Black Holes, Matters of Gravity. In stars, gravity holds a star together but is balanced out by repulsive electromagnetic force, fusion, or degeneracy pressure. If gravity completely overcomes these, a star just becomes a black hole where not even light can escape. To understand some of the properties of black holes, we have to talk about Einstein's theories of relativity, starting with the special theory and then moving on to the general theory. So, the special theory states that your description of physical reality is the same as regardless of the constant velocity at which you move, which is another version of Newton's first law in classical mechanics. And regardless of your speed or direction, you always measure the speed of light to be the same. Because speed is distance traveled over time, space, which corresponds to distance, or time, must change depending on your relative speed in order for this to be true. It turns out both warp based on the speed you are moving relative to another inertial or constant speed reference frame. In classical physics, we might expect that if a car was moving at 0.5 the speed of light, that the photons emitted from a stationary light source, or such as a lamp, would move at half the speed of light because you are moving towards the lamp at zero point 0.5 half the speed of light. However, what happens is that they move exactly at the constant speed of light, 3 times 10 to the 8th meters per second. What instead happens is that there is a Doppler shift, which is caused by the motion of the observer towards the photons and causes there to be a change in frequency of the photons or energy of the photons, but not a change in the speed of the photons. Some of the results of special relativity are Einstein's equation E equals mc squared, which states that mass can be converted into energy and energy can be converted into mass. The length of an object decreases as its speed increases. So if a train is passing by you that has an initial length of 20 meters, if it's going fast enough, if it's going close to the speed of light, as it passes by you, it might look like it's only 14 meters long. Clocks that you see as moving run more slowly than you do clocks at rest. This is going to cause the clocks, if 1 second passes in the reference frame of something that is moving relative to you, then maybe half a second passes in the reference frame of you who is stationary relative to the moving reference frame. And the mass of an object increases as it moves faster. So E equals mc squared, you pick up something called kinetic energy, which is the energy of movement. And because energy is equal to mc squared, the mass of the object increases in order to gain this kinetic energy. As the kinetic energy increases, mc squared increases. For the general theory of relativity, instead of just talking about inertial reference frames, it also talks about accelerated reference frames and gravitational effects on space-time. So Einstein believed that being in a gravitational field was identical to being in an accelerating, changing speed over time, a reference frame, because moving at different speeds caused a warping of space/time, or space-time. It makes sense that being in an accelerating reference frame would as well. Because this is seen as identical to a gravitational field, gravity, or the presence of mass that causes gravity, warps spacetime as well. The warping of spacetime by mass is actually what causes gravitational force in this point of view, like two objects being pulled towards each other on a warped sheet of rubber. Greater concentration warps spacetime more and causes a slowdown in time. In addition to matter, curves in spacetime also draw in light. Light travels along geodesics paths of least length rather than straight lines through the curved spacetime. Photons that leave the vicinity of a star also lose energy in climbing out of the star's gravitational field. They do not slow down like a bullet fired upward, rather they shift to longer wavelengths, an effect we see in the spectra of some white dwarfs, for example, whose light appears redder than it would if this effect did not occur. Some of the predictions of general relativity is that light is measurably deflected by the gravitational curving of space to the presence of matter like stars, or entire galaxies containing billions of stars. The perihelion of Mercury as seen from the Sun shifts or precesses by 43 arcseconds per year, more than is predicted by Newtonian gravitational theory. Its actual precession is exactly the amount predicted by general relativity. The orbits of stars in binary systems follow the paths predicted by general relativity rather than those predicted by Newtonian gravitation, and the spectra of stars are observed to have the gravitational redshifts predicted by general relativity. Let's now return to stellar evolution and consider what happens when a high-mass main-sequence star with more than 25 solar masses explodes as supernovae. As with main-sequence stars that have contained between 8 and 25 solar masses, high-mass stars become neutron stars. The neutron remnants of these high-mass stars have more mass than the gravitational force of the neutron star overcomes by the neutron degeneracy pressure created by the interactions among its particles. As a result, such remnant stars collapse further, and no force in nature can stop their infall. They are called black holes because they capture all of the light that comes out of them. Instead of radiating out and bending somewhat back towards the star, all of the light in a black hole is going to radiate, or all of the light that would be in a black hole would be pulled straight back towards the center of mass at a boundary of the black hole away. These regions out of which no matter or any form of electromagnetic radiation can leave are called black holes. Plummeting in on itself, a collapsing neutron star becomes so dense that it ceases to consist of neutrons. General relativity predicts that in creating a black hole, matter compresses to infinite density and zero volume, a state called a singularity. However, we know that general relativity and other theories of physics are invalid in such a speculation. A more comprehensive theory of nature must be developed to explain the state of matter in a black hole's singularity. Efforts are underway to develop such a theory. The best known nascent explanation is superstring theory, but it does not make testable predictions in this realm. All we can say with confidence is that the matter in black holes becomes incredibly dense and compact. A black hole is separated from the universe by its boundary, the event horizon. The distance from the center of the black hole to its event horizon is called the Schwarzschild radius, after the German physicist Karl Schwarzschild, who first determined its properties, and is given by 2 times g times the mass of the black hole over the speed of light squared, where g is the proportionality constant of Newton's theory of general gravitation. And if the mass of Mount Everest were compacted into a black hole, this Schwarzschild radius would be about 10 to the negative 15 meters long. General relativity predicts that all the mass is in such a black hole, a non-rotating or Schwarzschild black hole, collapses to a point of infinite density at its center, the singularity mentioned earlier. The rest of the volume from the event horizon to the singularity of a Schwarzschild black hole is empty space. You also have rotating or Kerr black holes. When the matter that creates a black hole possesses angular momentum, that matter collapses to a ring-shaped singularity located inside black holes called its center and the event horizon. Such rotating black holes are called Kerr black holes. In honor of the New Zealand mathematician Roy Kerr, who first calculated their structures in 1963. Once again, the black hole is empty except for the singularity. Most Kerr black holes should be spinning thousands of times every second, even faster than the pulsars that we studied earlier. This is because the core mass from the rotating star that creates the black holes is contracting, and to conserve angular momentum must spin faster, like the figure skater who pulls their arms in closer to them and starts spilling faster. Kerr black holes cause nearby space to spiral around them like water in a drain. Whereas an object released from rest in the vicinity of a Schwarzschild black hole would fall straight into it, the same object released near a Kerr black hole would spiral inwards. The equation of general relativity revealed that a swirling region of space called the ergo region, immediately outside the event horizon of each Kerr black hole, forces all objects at rest in that region to fall into the black hole. It is moving fast enough sideways. An object that enters the ergo region can fly out of it. However, if an object stops in the ergo region, it must fall into the black hole. If you bring a cube that is emitting blue light near a black hole, then as it comes closer, it will start warping like you see in this diagram, and the light that is closest to the black hole will lose the most energy, causing it to become red, while the light that is a little farther away will be a little oranger. But both of them are going to lose a lot of energy and be warped a lot. It's just that the closer you are to the black hole, the more warped your spatial properties of the blue cube will be, and the more warped the time properties, where it will appear to be moving a lot slower near the black hole than it will look to you outside of the black hole. Whenever any matter or energy such as photons moves, the shape of spacetime, often called the fabric of spacetime, changes shape. Under the right circumstances, such as a pair of objects rotating around each other, the motion of matter or energy can send out ripples of changing spacetime that travel at the speed of light. These ripples are called gravitational radiation, and the waves that result are called gravitational waves, colloquially called gravity waves or ripples in the fabric of spacetime, and they have recently been discovered. I don't even know if they had been discovered quite yet, or if they had, it was within a year of this book being published. But in order to detect them, because these gravity waves cause such a small change in distance, you have to have huge detectors, such as LIGO, which is our main detector, where you have one detector on one end of the United States and one detector on the other end of the United States, and you compare the motion, or you compare the movement of these two detectors in order to be able to pick up the really, really infinitesimally small changes in space-time that you're going to see from gravitational waves. There are also other types of black holes. Early in the life of the universe, black holes form from the condensation of vast amounts of gas and also from the collisions of stars during the process of galaxy formation, thereby creating supermassive black holes. Most of these black holes have masses between 1 million and 20 billion solar masses, with the most massive one known to date having 66 billion solar masses. We saw in the section earlier that stars form in clusters. If a cluster forms with enough stars concentrated in a sufficiently small volume of space, collisions between stars at the center of the cluster may lead to the formation of a black hole between a few hundred and a few million solar masses. Such objects are called intermediate mass black holes. None of the observations of potential intermediate mass black holes have yet been confirmed, and black holes could have formed during the explosion beginning of the universe as tiny amounts of matter were compressed sufficiently to form primordial black holes. These bodies would have masses ranging from a few grams to the mass of about a planet. Black holes can also be in binary systems. Consider a black hole, which is analogous to a neutron star in a binary system. A companion star is still fusing material, then its outer layers can be pulled off, as discussed earlier. The inflow of this matter towards the compact companion is too rapid for all of the mass to enter the event horizon immediately. The resulting accretion disk around the black hole is the key to explaining the presence of jets. As the disk mass spirals down toward the event horizon, this gas is compressed into smaller volumes. Such compression heats the gas, which in turn causes its pressure to increase. As a result of the increased pressure, the gas expands, forming a donut-shaped region around the black hole. As the gas starts in the final plunge into the black hole, its temperature skyrockets to tens or even hundreds of millions of kelvins. At such temperatures, the pressure is so great that much of the infalling gas expands, and finding little resistance perpendicular to the plane of the accretion disk, it squirts out as two jets. These jets are prevented from spreading out by a magnetic field created as the hot gases orbit the accretion disk and by pressure from surrounding gas. Astronomers have measured the speed of this gas to be as fast as 3% of that of the speed of light. Black holes are also predicted to evaporate. Black holes convert their mass into energy by a process called virtual particle production. If things in this chapter aren't weird enough, consider this. The law of nature allows pairs of particles called virtual particles to spontaneously appear. Each pair consists of a particle and its antiparticle, such as a proton and an antiproton, an electron and an anti-electron, or a positron, or a pair of photons, where photons are their own antiparticles. The particles in each pair are identical except for having opposite electric charges, and they annihilate each other and normally disappear without a trace within a very short period of time, typically 10 to the negative 21 seconds. However, two virtual particles from just outside the event horizon of the black hole, they would experience an exceptionally powerful gravitational field. If one particle is created slightly farther from the hole than its companion, the two virtual particles feel a tidal force from the black hole's tremendous gravitational pull. If the gravitational tidal force is strong enough, it can pull two separate particles apart before they can annihilate each other. This separation makes them real. To conserve momentum, at least one of the newly formed real particles always falls into the black hole, but the other particle will sometimes have enough kinetic energy to escape the vicinity of the black hole. The latter particle flies free into space. Because the gravitational energy used to make the virtual particle real came from the mass of the black hole, the hole loses mass equal to where m is equal to E equals mc squared, where m is the mass of the freed particle and c is the speed of light squared, or if the pair of particles are photons, where the wavelength of the departing photon is F, and H is Planck's constant, and the energy is H times F. The energy from inside the black hole is transmitted outside the event horizon as gravitational radiation to replace the energy taken away by the newly formed particles. This is called the Hawking process, and the particles leaving the vicinity of the black hole are called Hawking radiation, even though many of the particles are not electromagnetic radiation. As a result of the Hawking process, the black hole loses mass and eventually evaporates. Some colliding stars, black holes, neutron stars, and the supernovae that accompany their evolution are apparently the source of the most energetic and enigmatic emissions known in the universe, called gamma ray bursts. These pulses of gamma rays, the shortest wavelength of electromagnetic radiation, emit more energy than supernova, even from smaller volumes of space.